Welcome to the second installment on the periodic table in regard to the periodic trends. The focus of this video is going to be on ionization energy and on electronegativity. Now remember, when we talked about atomic size in the previous video, I identified the fact that when we talk about these trends, we look at what's going on two different ways. One way we look at the trend is from the top down in any given group. Top down in any given group. The other way we look at trends is left to right across the periodic table or across any given period. So for example, if we want to make comparisons in regard to the size of various elements, we might want to compare lithium, for example, with fluorine. And so we would make this comparison across period number 2 from left to right, this being lithium and this being fluorine. And remember that in terms of atomic size, the size decreases as we move left to right across the table. So there's going to be two fundamental ways that we look at the trends of ionization energy and electronegativity, from the top down in any given group and from left to right across any period. Now, we're going to focus on ionization energy first. So what is the definition of ionization energy? Ionization energy is the energy required to remove an electron from a gaseous element, a gaseous neutral element. There are going to be two trends. Now, we'll start by talking about the trend moving down any particular group. And before we do that, I want you to remember something. As we go from hydrogen to cesium, each time we move down to a new element, we've added subsequently a new energy level. So lithium is a thicker atom than hydrogen, and sodium is a thicker atom than lithium and much thicker than hydrogen, and so on. I also want to call your attention back to the group number. The elements in group 1 all have a single valence electron, which is on the outer surface of the atom. So remember, what we're talking about right now is ionization energy. That is going to be the energy required to remove an electron from the outer surface of an element. So as we move down the group, the valence electron in group 1 is being pushed further and further and further away from the nucleus. So cesium's valence electron is much further away from the positive charge of the nucleus than hydrogen's single electron on the surface of hydrogen. So as we move down any particular group, it becomes easier and easier to remove the electron. Or another way to look at it is ionization energy will decrease as we move down any major group on the periodic table. So that would include groups 1A and 2A, and then 3A through 8A. All right, so once again to reiterate, when we move top down in a group, ionization energy decreases. It becomes progressively easier to remove an outer electron as we move down a group. Now, what about moving left to right across the periodic table? What you need to remember about this phenomenon that we're talking about now is you must reach back and reconsider the argument that I made about size. We know that going from lithium to fluorine, that the atoms become smaller. And that was for two reasons. The most important, perhaps, well, they're both equally important, but one of the things you need to remember, one of the reasons for this is because as we go from lithium to fluorine, the nuclear charge is increasing because we are progressively adding more and more protons, Here we go from boron, which has got 5 positive charges in the nucleus, to fluorine that has 9. And the second factor that was involved in the size issue was the fact that as we move left to right across this period, or any of these periods, we're adding electrons to the same exact energy level. So those electrons that we're adding are the same distance away from the nucleus. So we need to now relate this idea back to ionization energy, all right? Because what the trend tells us is as we move from lithium to fluorine, the ionization energy is going to increase. That should make sense to you because the nuclear charge that exists in the nucleus of the atoms as we go left to right increases as we move across the period. And this increases the attractive force that the nucleus has for its outermost electrons. So it follows from that it's going to be progressively harder to remove an outer electron from any atom on the table as we move from the left to the right. Now, the next trend that I want to talk about, the last one actually, is called electronegativity. And this trend is it's easy to understand as far as applying the trend to the table, which I'll state in a minute. But it's a little bit harder to understand the definition of this particular concept. All right, so I'm going to give you the definition now in words with an example, and then what we'll do is we'll come back and talk about the trend. So the definition of electronegativity is the following. It is the attraction that an atom has for bonding electrons within the bond that atom has with another atom within either an ionic compound or a molecule. So let's just talk briefly about what this means. So on the board I've got two different types of compounds. The top compound is an ionic compound composed of the metal sodium combined with the nonmetal bromide. In this case, in this particular kind of compound, an ionic compound, the electrons are not shared. And in fact, bromide retains most of the electronic density, if you will, of the electrons that exist between the sodium and the Br. All right? In an ionic compound, the electrons are not shared to any extent. And that's because two different atoms have been combined to form a compound. And those two elements have dramatically different attraction for electrons when they are sharing those electrons with another atom. So when sodium bonds with Br, the two electrons that exist between these two atoms are not shared equally. They are withdrawn almost completely to the Br, forming Br minus, leaving the sodium completely ionized as Na plus, and it is the opposite charges, the force of attraction between opposite charges that holds these two ions in an ionic bond. All right? So Br is more electronegative than sodium. It has the capacity to attract electrons to a much greater level than sodium when the Br is combined with sodium in a bond. Now I want to draw your attention to this covalent compound, or this molecular compound below. This is chloromethane, and it's a compound that's composed of carbon, as you can see, of carbon, hydrogen, and chlorine. Now, the dash marks mean that the carbon is involved in a covalent bond with each of the three atoms of hydrogen and the one atom of Cl. The dash indicates that there are two electrons in the bond between the C and the Cl, and between the C and any of the other H's. Now, these two atoms, the carbon and the Cl, do not share electrons equally. And the reason they don't is because chlorine is more electronegative. What that means is, when you combine Cl with a carbon, the Cl has a higher degree of attraction for the two bonding electrons that exist between these two atoms than carbon does. So the electron density is shifted towards the Cl. Now, this is a very important concept to chemists, because later on we're going to use this idea in order to determine whether or not a molecule or a compound has a property we call polarity. This is not something that we're going to be worried about right now. But later on, you will have to be able to evaluate a molecule based on its electronegativity differences. All right, so let's see how this trend is going to work. All right, so again, we have two different trends. We have two different directions, from the top down and left to right across the table. So we're going to take the top down example first. So moving down any particular group, electronegativity decreases. And the reason this does is pretty simple. It's just because your surface electrons, once again, are very, very far away from the atomic center of that atom. So as we go from hydrogen to cesium, the cesium atom is much fatter. The single electron that we have in the valence is very, very far away from where the nucleus is. And when cesium is involved in a bond with another atom, it has very little attraction for that outer electron. All right? So electronegativity decreases down any group. Now, on the other side of this coin is when we move left to right across the periodic table. And what we have in that situation is distinctly different from moving down a group. Electronegativity increases going left to right across the table. And it turns out that fluorine is the most electronegative atom on the table. And what does that mean? It means that when you combine fluorine with another atom in a bond, it has or will demonstrate the majority of the attraction for the bonding electrons within the bond between those two atoms. If we compare carbon to fluorine, fluorine is more electronegative than carbon. So if we combine carbon in a bond with F, the fluorine is going to attract most of the bond density, most of the electron density towards itself within that bond. Or in the example I showed here, you can see that Cl falls to the right of carbon on the periodic table. Chlorine is more electronegative than carbon, so when this atom is combined in a bond with carbon, Cl will have the majority of the attraction for the electrons in that bond, and those electrons will be withdrawn towards the Cl, providing it with ionic character.